Okay, in our last segment, we saw, and I'm going to try to do this relatively neatly but quickly, we saw that when we graphed y equals the sine of x, that the period of the sine of x was equal to 2 pi radians. And so I'm going to go ahead and sketch a real long looking version of the sine of x, where this is 2 pi right here, and this is pi. I'm not going to put the other coordinates, the x values. Then, in our last segment, we graphed by hand y equals the sine of 2x, and that curve finished its cycle in pi radians, so it ended right here. And I'm going to go ahead and put 4 equal points here to help myself sketch that curve. So it started here, it hit the high point of 1 right here, then came back and crossed the x-axis. It went down to a -1 right here and finished right here. So that curve looked like this. And again, it finished, its period for the red curve was pi radians, the time it takes to complete one cycle. Well, what I'd like you to do, and I'd like you to pause after you've heard me out here, is I'd like you to put the sine of x into your graphing calculator. Then I'd like you to put the sine of 2x into your graphing calculator, and then the sine of 4x. And you know what? On second thought, let's take it back. Let's just put these two in. And would you remember, please, to, once you've put them in, to hit the zoom key. And under that, would you select probably number 7 for zoom trig. So it gives you a decent window. So go ahead and graph that. Okay, you're back with me. And I think, and if you have a new graphing calculator and it was in color, you know how the period of this red curve was pi because we had a 2 in front? So we cut the original period in half to get to here. Did you see when you graphed the sine of 4x, which I'm going to go ahead and do in blue, that its period, and I've got to label these so I can make sure I don't make a mistake. This is pi over 2. I believe its period was finished right here. So I'm going to put 4 equal points in right here. So you saw this curve top out right here. It came back and crossed right here. It bottomed out right here, and it crossed the x-axis at pi over 2. And again, it started at 0, 0. So it got quicker. These curves are getting quicker as the number in front of x increases. So we had a 2x here, now a 4x here, and the period of this function, the sine of 4x, turned out to be pi over 2. So this second function's period is pi over 2. So can you create a definition now for the period of a function? And I would like the definition in terms of, let's keep with sine, y equals, we have to keep this a in front of the sine of x in case the amplitude changes. But in terms of this letter b, can you write a policy, if you will, that would describe how you would always find the period? Remember, the basic sine function is 2 pi. Always 2 pi. When you put a 2 in front of x, it got down to pi. What did you do to this to get it down to this? And if you put a 4 in front of the x, look at how many cycles of this you could get, this blue curve you could get in one sine curve. So there's a second curve, and then here's a third, and here's a fourth curve you get with this 4 in here. So haven't we quartered the period from this in terms of the amount of time it takes to complete one curve? So the definition is to always take 2 pi, the original period for the sine of x, and divide it by the variable b. That's supposed to be the letter b. That's the number in front of x. So now, and don't forget, you can check these with your graphing calculator, the period of this function where it's got a 6 in front is that you get 6 cycles in the time that you would get 1 cycle if it was just cosine of x. So you divide 2 pi by 6, and you reduce that, please, to pi over 3. And then when you go to graph this curve for me now it's going to be a sketch. I'm just looking for a sketch of this curve. So remember, the amplitude in front of this one is a 1. So all cosine curves start high, if you will, and then they go down to the x-axis. Then the wave is down below, and then it comes back up, and this is where it finishes, and this is where it would start to repeat. I'm going to use another color. So it would repeat right here and do the cycle that I just did. All right. What I care about is that you sketch one full cycle, and the period for this function is pi over 3. So to go from top to bottom to top again is pi over 3. So what I need now is I need you to give me these points right here, and they are all they're all equal distance, and they're a quarter of the period. This distance is a quarter of the period. This distance is 1/4 of this. So is that, and so is that. So these key points where it crosses the x-axis, it goes down to a -1, it crosses the x-axis again, and it tops out at 1 again, are a quarter of the way. What I'll often do to find these points is I'll get this one, and it's a half of this one, because here's pi over 3, so this is halfway. So half of pi over 3 is pi over 6. And now what I notice is that to take half of this, all I got to do is multiply that by 2 to get that. And this point right here is half of this distance. So pi over 6, if you take half of it, you just multiply that denominator by 2, and you have pi over 12. That pi over 12 is also a quarter of the period. A quarter of the period, which is pi over 3, is pi over 12. That's the distance from here, and then you add pi over 12, and you add pi over 12, and you add pi over 12. So finally, if you would ever just like to find a quarter of the period, because in order to get here, you would have to take 3/4 of the period. So to get that spot, you'd take 3/4 of pi over 3, and that would, and notice that those 3's would cancel out. So it'd be a lot easier if I just do that right now. And that last, the 3/4 spot is pi over 4. I'm going to show you an easier way next time to find these quarter points, but I need these. I need these quarter points. Please also notice that as this number gets bigger, the period shrinks, but as this number gets smaller than 1, the period grows. So the period is defined as 2 pi divided by b, and when you divide with fractions, you multiply by the reciprocal. So when you divide by 1/4, you multiply by 4 over 1, or just 4. So the period of this curve is 8 pi. I'm going to need to erase a little bit right here in order to do this work. So again, the period for this sine curve is 8 pi. So I'm going to try to drag this out a little bit. So as this got smaller, it's a slower sine curve. Much slower sine curve, where the amplitude is 1. But the period way over here is 8 pi, when this is 1/4. So now I got to go and find that spot right there. Well, it's half of this, so that's simple to see that's 4 pi. And then this quarter point right here where it tops out is half of 4 pi. That's 2 pi. Oh, yeah, 2 pi, 4 pi, 6 pi, and then 8 pi. I can tell I got my quarter points correct. I tried to draw this out longer as opposed to this skinny wave, so that just to exaggerate that the period is much greater now. Let's do this one more time. Now these problems just said what's the period of the function. That's all they wanted you to find. They didn't ask you to actually graph it, but I'm going to go ahead and keep doing it. So the b value in front of this problem right here is the pi. That's the number in front of x. So it's a 3.14. But when I divide this equation by pi, I get a period of 2. So I need you to know that these x-axes values, this 2 pi, 4 pi, 6 pi, 8 pi, they're just numbers. It's just that before they've had pi in them. And this particular curve, y equals the sine of pi x, is a sine curve where the period is 2, so halfway is 1, and half of that is a half. So these increments are halves. Half, then up to 1. Here you're at 1.5, or you could call it 3 halves, and then you're up to 2. Don't forget the amplitude is 1. And don't forget that -1 down below. So most of our concentration here is to graph these without a graphing calculator, but I want you to use a graphing calculator, so that's not an issue. I'm going to ask you when we come back to tell me the period of the function, create a sketch, and make sure to label the quarter points. But we're going to mix up sines and cosines and add amplitudes as well.